pleased to introduce our speaker today, Dr. Iain Duff, a numerical analyst like Sam Conti. Iain is a pioneer and leader in sparse matrix computations, an area of great relevance to computational science and engineering. Many of the algorithms developed by Iain and his research group are contained in the excellent Harvard subroutine library, which I recommend to you. Iain obtained his PhD at Oxford and currently is a senior fellow in the scientific computing department at Rutherford Appleton Laboratory in England. He is also the scientific advisor for the Parallel Algorithms Group at Surfax, Toulouse, France. Iain has a long list of honors and awards, including Fellow of the Royal Society of Edinburgh, Fellow of the Society of Industrial and Applied Mathematics, and a Life Fellow of the Institute of Mathematics and its Applications. Welcome, Iain.
Oh, my. Well, Ahmed, thank you very much for that introduction. I'm not sure how the audible thing is going. This is meant to be for some taping. That's working there. But you can hear me okay, people. That's fine, I hope. Right, so once I've worked out how to do this technology, I'll continue. So let me say that it's a great pleasure, and thank you very much for inviting me. It's only my second visit, I think, in my life to Purdue, and the last time was a long time ago, and any of you who are graduate students were surely not even born at the time I was last here, which is very embarrassing for me. But some things have changed. There's about 200 times more buildings in the Purdue campus than there used to be, but otherwise life is similar. I think there was a storm that came through last time I was here. So it did make for an interesting visit. Sandwiching myself between Sandy and the presidential elections was an interesting time to come to the US of A this time. And I was delighted that I booked my flight through Chicago and not through New York, which would have been an alternative way of getting here. So let's see if we can get off to a good start. Yeah. So I should say that, unfortunately, I don't remember meeting Sam Conti when I was here in my last visit. I don't think I did. So I don't think I've ever met him. But that doesn't mean that he hasn't been an influence in my life. And this book was actually a very, very popular, at the time I was a student in Oxford. This was a very popular book for not just numerical linear algebra, which is my field, but for many, many aspects of, well, as it says, elementary numerical analysis. So this is a copy taken of the cover of a book, which I still have in my office to this day, in which I used. The first edition of this book was 1965, and the second edition, and I used the first edition, I think, and then in 1972, I splashed out and bought a second edition. Well, it's a bit fast. And let me just say that this was really an avant-garde book at the time. I mean, you say a book in numerical. I mean, this is one of the very first ones that what it says a completely computerized approach to numerical analysis. 65, the book was. That was really advanced then. And indeed, the programs, and I had some jokes about Fortran and other programming because I knew this is a computer science department, but in the interest of not trying to overrun more than about 3 hours in my talk today, I've taken some of the Fortran comments out. But let me say that I still use Fortran language, and I was really pleased to see that the originator of your department here 50 years ago in Purdue, who was a numerical analyst, as Ahmed mentioned, also was a great Fortran programmer, and even Fortran 4, which is sort of like ancient Greek in the programming language curricula. And the machines themselves also, they are more like ancient Roman, I guess. So it goes back a long way. So here's an outline of the talk. I'm making a few irreverent, well, I've already made some irreverent remarks, maybe, and I'll make a few more. Then I'll mention something about Exascale, because that was in the title. maybe a bit irreverently as well. And then I become more serious because it's my own research area. I'll talk about solving linear systems, in particular sparse linear systems. Then the main theme of the talk is the sort of hybrid methods. And then, and I actually genuinely doubt I'm going to have, good, there is a clock here, that's good. I genuinely doubt that I'll have much time to dwell on it, is the BlockCamino method, but I would hope to at least introduce that to you if you're not familiar with it, and then a couple of conclusions. So I really started in parallel computing as a disciple of people like the present Samuel Conte professor, Ahmed, sitting there, Ahmed Sameh, and David Cook and others at the Center for Supercomputing Research and Development, which was in Illinois. I can never remember whether it's Urbana-Champaign or Champaign-Urbana, but one of these places down a rather fast journey south of Chicago in a little prairie land village called Urbana-Champaign. And that was really very influential for me. The project that they had running there at the time was called the Cedar Project, and that was very, very advanced at its time, and in fact has really an inkling of what we're talking about when we move to Exascale, but things have moved on a bit. But it was a hierarchical system linking multiple Alliants. Alliant was one of the real manufacturer who produced a usable parallel computer in about 1985, and that was remarkable and was in fact the first machine that I used. I've already got into a row by mentioning things like LinPack today in discussion, and I'm not going to dwell on that, but just to say that the Alliant was actually fairly advanced at its time for the amount of money that you spent. So it was a little bit less powerful than a Cray 1, which preceded it by 10 years, admittedly. And the megaflop peak was roughly about the same as I can get out of my iPhone here now. So that was in these days very, very, very advanced, actually. In fact, we attained, the towards peak performance was attaining a reasonable percentage of the absolute megaflop peak. So this really was an exciting time for parallel computing, because as you'll see in a minute, there was many people producing the machines, and they were selling them or trying to sell them, let's say. And then I hadn't realized that somebody told me that Geoffrey Fox is now up the road in Bloomington, which I hadn't realized, but at one time he was in Caltech, and this is just to give a date on it, and he said this is the first year of the parallel supercomputer. And certainly that was the heyday, and there were many companies. Oh, I had a definition of supercomputer. This is me being a bit scurrilous again, a bit irreverent, and I think it's actually valid almost to this day, that a supercomputer, a high-performance computer, is one whose hardware is at least one generation in advance of its software, and this is going to be one theme that I'll have in today's talk, and it's a serious theme, unfortunately, as many vendors have discovered to their cost. And here's part of the cost. Here's a list of supercomputer companies round about the time that Alliant started. Alliant's not on this list right now. The very first supercomputer that I ever programmed was called the Denelcore HEP. There was one at Argonne at the time. But alas, what happened to these is that they all disappeared. Within 3 years, none of them were left. Nearly all the companies had all folded. FPS continued a bit, and some other companies struggled for a little bit. But really, they had a very, very short lifespan. They started around about mid-80s, and they were all dead by 1989, essentially. And it was very fierce competition. So here, I thought this was quite ambitious and amusing to have letters that said we will win it. The ETA 10, and the strength of this, we bought one in my center in Toulouse, on my advice partly. This was 1987, if you can see the date there. ETA systems ceased to exist by 1989. And indeed, this was a list of computers, supercomputer companies now in 1988. The ones in red are all ones that I persuaded Surfax to buy. And we began to think that nobody would sell us a machine soon, because every time we bought a machine, the company folded in about 2 years' time. There was a lot of innovative things. So BBN, for example, developed a software called TotalView that's still, in fact, used today in helping to program parallel machines. So there was a lot of good things come out of that, but they all folded. So that's the sort of background, if you like. And to my mind, some of the earlier failure can be summed up like this, that there's market forces, if you like. So venture capital built up, gave you the machine, and then it came down because of lack of software. And really, I think this is something we have to learn. Otherwise, we'll repeat the sins of our fathers, as I'll mention in a minute. So we want to avoid that. So we don't want to go that way. So we want to get some software in place as one of the models of the tale here. And because I work in Surfax, I have to try a little bit of French to people here. But I noticed that we're in Lafayette, or West Lafayette at least, so I guess most of you are bilingual, and that's fine. And so all this means is that nothing changes, really. You're going through the same things again, or there's various nice interpretations. And I actually like the French better than the English, because you can have different ways of translating it. And it really means it's the same sort of thing, where we've looked at this before, and have things changed? They have in many ways, they haven't in other ways. And do we want them to change? Yes, we do in some ways, of course, because we want to have things that will work. So what's happening now? This is on to the exascale, or the future exascale. So exascales 10 to the power 18, as you know. Floating point, well, the normal definition is 10 to the power 18 floating point operations per second. About 1,000 times, roughly, maybe not quite, nearly 1,000 times faster than any machine you would likely to buy today. The vendors, IBM in particular, will tell you they could give you an exascale machine tomorrow. You may not be able to house it easily, and you may have to switch down everything else in the state to run the thing. The best estimate of, well, we'll come to that in a minute, power consumption is quite high. We'll come to that in a second. So that lack of venture capital might be a bonus, and there's only a few big players. In fact, according to the IBM guy that was talking to this other day, there's only one player, whom you can guess whom he was suggesting. But in fact, there may be a few more. But really, we don't have the proliferation of companies as before. It's really changed. So that's a plus a chance thing. Most of the technologies are kind of in place. There's a lot of technology in place anyway. And really, I'm not going to tell you what an exascale machine is for two reasons. One is I don't know. Second is if I did tell you, or if I pretended to know, or if you pretended to know, you could well be wrong. It could well change. But one essence is that there'll be, has to be many levels of hierarchy in your machine. There'll be elements of multi-core, elements of GPUs, and the buzzword that I'm using is this hybrid, and you'll see this appearing more than once in the talk. It's a hybrid architecture. So I just mentioned early on is one of power consumption. This has been a big issue. Now, almost the best machines, the best petaflop machines we've got today, best class of them from a point of view of memory, of power consumption, are the IBM Blue Jeans. They're really very good for power consumption. But even if you were to expand that to exascale, you'll be looking at over 200 megawatts to run the thing, which is $200 million a year just to run it, and the electricity. And you have to find 200 megawatts as well to run it. So the target that DOV and others have suggested for manufacturers is 20 megawatt consumption. So that's a bit of an improvement, a bit of a change. So that is the one issue that's causing some concern just now with the vendors. And perhaps, the vendors are still gung-ho that there'll be a machine round about 2020 of this power. So we'll see. But I'm not discussing the hardware today, really, as you can see from my background and my talk. But I should just make one mention of power consumption, which is quite amusing. We have a sister laboratory to Rutherford, which is called Daresbury, which is near Manchester in the rainy part of England. Yes, I mean, if you yes, if you want to visit Manchester, do take a raincoat, I recommend. In that lab, there used to be a thing called SRS, a synchrotron radiation source. So this was, you would spin electrons round and get X-rays. And this became redundant, really, because they built a new one down by us at Rutherford, the diamond source. And so they closed the SRS. And had it not been for them closing the SRS, they couldn't have bought and used the new supercomputer they've just got. So they've got an IBM Blue Gene and some other IBM Dataplex machine, which actually is, they're very proud to say, is the 13th on the top 500 list. But that's the main thing, is it's the biggest machine in the UK, bigger than the main academic machines. So they're very proud of that. And I mean, it really is terrible, but the managers are like schoolboys when they're competing that way. Anyway, that machine would not have been able to run at Daresbury if they had still had the SRS running because of the amount of power consumption. The total power that the lab has there is 6 megawatts. That's all they've got. And one of the things they're now doing right at the moment is increasing that to about 20 megawatts for the whole lab. So you can see there are issues. Power consumption is a big issue. So moving on towards the software support, well, so there's various levels, and there's various levels of support. And I'm mentioning ones that I use myself, but there are lots of other sort of mirrored things. But I use multi-threaded basic routines, BLAS and that. I'm a Fortran-based person. I tend to use OpenMP with Fortran and MPI. We can use that. And you have to really use them all. And the other term that's quite often used here is hybrid computing. So that's the second time we've seen hybrid. We've had hybrid computers and now hybrid computing. So we're going to have a third one soon. Just want to make a couple of mentions about the software. This was the so-called International Exascale Software Initiative. Used to have great meetings all over the world. Not quite sure exactly what it achieved, but it was at least trying to focus on an important issue. And it started in 2009, and the major people involved were Pete Beckman from the Argonne in Chicago and Jack Dangara in Tennessee, and it's been completely cut by DOV. And you can work out whether that's a bad or good thing. I think it's actually a dangerous thing if it's signifying that the DOV is not supporting software because as I said, the sins of the fathers, if you don't support the software, you're going to have big trouble when these exascale machines come. Anyway, if IESP has done nothing else, it's provoked Europe into making a response, and it inspired, as I mentioned there, this European version of the same type. And that's the European Exascale Software Initiative. And I was quite involved in that, and we did our final report in Barcelona in 2011 in the autumn there. And we got funding then from the EU, who were very supportive of our results, but they didn't give us the billions of euros that we were requesting. But they have given us a couple of million to look further at trying to develop a program for them to fund over the next 10 years or so. And it's quite amusing. I've met people this week who are actually involved in projects with Total. They seem to have a lot of fingers all over the world. That's the big French oil company, if you don't know. So Total and Prace, which is the major consortium, if you like, for supercomputing, mainly supercomputing hardware in Europe. They're supporting this project, and we just had our kickoff meeting September, well, I guess we're November now, so it's 2 months ago. Yeah. Yes, I should say Happy Toussaint. This is, I mentioned about Lafayette being partly French. This is actually a major French holiday on November the 1st. It's called Toussaint, All Saints it means. And I shouldn't really be lecturing here. I should be having a vacation. If I would have been if I'd been in France. So we had that meeting there. So now I want to move on. Yeah, we're not doing too badly. I want to move on to the main area, that is my research area, and try to then indicate how that fits in with the possibility of managing these monster machines that we may see in under 10 years' time. So so A, I should say, is a matrix. Now, Ahmed said that most of you would sort of know what a matrix is. I hope you do. Well, it's a system of linear equations, and if you don't know what that is, then I'm a bit worried. Okay, so the dimension of them is going to be in the millions, large, and the matrix A in particular is going to have mostly 0 entries. So this could, for example, be a discretization of a differential equation. It could be a large problem in structures. It could be something coming out of Facebook or one of these kind of social networking matrices. So you get plenty of examples of them. So there's 2 main techniques for solving these. One's direct methods, and I'm going to spend a little while on that. This was I would say, my major area of research for many years, and I still do research in this area based on matrix factorization. And, of course, iterative methods, and I'm going to very briefly define what I mean by these two in my sense. So the essence of a direct method is that you do a matrix factorization. It doesn't have to be an LU. It doesn't have to be Gaussian elimination. It could be other factorizations. It could be orthogonal factorizations. It could be other more kinky ones that people seem to keep inventing. But this is the one that I'm normally involved in. And the intention here and the main thing is to try and keep these factors, which are used in the solution scheme, these factors to try and preserve sparsity in these. Because if you're not careful, these could end up not being very sparse, even though A is. So that's the important thing, and I'm not going to go into detail of that. That's definitely another lecture. But I want now to mention that direct methods are really quite powerful. So this is on regular, like a kind of Laplacian type matrix, for example, 2 dimensions and 3 dimensions. So the order of the matrix here is k squared or k cubed. And I want to point out a couple of things. One is that the work for solving, after you've done the factorization, that's the what I was showing there, once you've done this factorization, the work for solving the system is proportional to the entries in the factors. So this last column is really the work for solving systems. And you can see that in the 2-dimensional case, it's almost linear. There's a log term, okay? And in the 3-dimensional case, it's k4th rather than k cubed. So it's not linear, but it's pretty good. And I should say that these types of problems are actually not the best problems for direct methods, because I'm looking at square or cubic grids, and they really aren't the best for handling them. So we're not looking at the best case scenario. No, I won't say that because I'll disprove myself in a minute. No. So the other thing is that the work for factorizing it, okay, it's certainly not linear, but it's here k cubed with a k squared matrix and k to the 6th with that. So it's not ridiculous to think of trying to solve particularly 2-dimensional problems using direct methods. Well, I mean, this was the holy grail for ages, and of course, to some extent, you could prove, and people did prove, that the complexity I showed on the previous slide is optimal. But essentially because you end up reducing it to a small, dense problem of order k here or of order k squared here, and that's where you get these figures coming from. And in some ways you can't avoid it, you think. So is there an order n method? Well, it's developing. So for problems, and this is for a lot of problems, many differential equations, you get a low-rank approximation because essentially everything's decaying away from the diagonal. I don't know how many of you are from math department, but if you think of a Green's function, it's got full support, but it's dying off. It's stronger locally. So if you look away from the solution, from the point you're at, it's dropping off fast. And you indeed can approximate, not only approximate, you can almost make it equal to a low-rank approximation. If you use these low-rank approximations, then you can develop, people have proved results in some cases that you can scale it linear with problem size. This is dramatic, and it's something I didn't believe 2 or 3 years ago. And I've been sort of convinced by it with some papers I've just been refereeing recently. And I should just mention, to give a plug for Purdue, that we have some people in Purdue who's here who are working on this kind of thing with other people in California. So this is actually, I think, a very exciting method. So I recommend chatting to him if you don't believe me. And just to mention direct methods, how powerful they've come. Now this is a problem of order about 1 million. It's quite a realistic problem. It comes from a car. Well, this you've probably heard of an Audi car. I suppose they sell in the US as well. They're not that cheap in the UK, but maybe they're cheaper here. German-based car, and this is from Body Panels. And it's a positive definite matrix, but it's actually badly conditioned. It's a nasty matrix, and it's now a standard training problem. And I think back in the old days when we thought 20,000 was a large matrix, you know, this has quite changed. Now, I think people know that you can't get a Nobel Prize in mathematics. So the question is, can you get a Nobel Prize in direct methods? Well, there's a person called Harry Markowitz, which some of you may have heard about if you've ever done anything, if you've gone to lectures by anybody in sparse direct methods, even at the most elementary level. And in 1957, he proposed, he's still alive, I think he's connected with Princeton now. In 1957, he proposed an ordering scheme for reducing fill-in. Now, fill-in was what happens when you look at the matrix A and the factors L and U. So he proposed a method, a very simple method, for keeping the amount of fill-in the factors for direct methods low, for keeping it low, for keeping the sparsity. Alas, that wasn't exactly what he got his Nobel Prize for, but it did in fact involve using things like this to get his Nobel Prize, and he in fact got it in economic sciences in 1990, and it was portfolio applications. But he was using essentially some of the software he wrote, and some of the software he wrote involved sparse schemes and using this. So that's the closest we've got to having a Nobel Prize in direct methods. So I'm only going to have 2 slides on these because this isn't the main area I've worked in, but I just want to mention that the type of iterative methods I'm thinking about are ones based on what we call Krill subspaces. Now, the thing that's nice here is that as I increase or I multiply essentially by my matrix A, I'm increasing the subspace that I'm trying to get my solution from. And there's a whole lot of methods, and basically what they do is they get better and better approximations in higher and higher subspaces until you've got a solution that satisfies, well, that's close enough to what you want. And depending on the norm, this is just a straight 2 norm of the residual, but you get A to the minus 1 norms, A transpose A norms, every kind of norm you can think of. Depending on that depends on the method you actually get. So this simple one is called GMRes, generalized minimum residual. And there are very many methods based on these Krylov sequences, right? Which is, as I keep increasing K and get a bigger and bigger subspace, and I'm getting the best approximation in some sense within that subspace. As I increase the subspace, of course, I'm going to hopefully get closer to the solution. So there is quite a simple, there's other iterative methods quite different, but these are the ones I would say most popular. Well, one of the problems with iterative methods are that this K, the K was the number of the dimension of the subspace. This K can be very large for the quantity you minimize them to be small. And what one does with iterative methods, what one has to do with iterative methods in general is to have some form of preconditioning, which is to change the system so that the new matrix I'm working on, in this case MA, has a much better, well, the eigenvalues are better organized so I can reduce K. It's as simple as that. And the matrix M is a matrix that I want to be able to easily invert or easily solve for. So there's a whole, the whole work of one of the main thrusts in iterative methods is developing good preconditioners. And it's interesting to note that in conventional preconditioning, some of the main techniques, so ILU stands for incomplete LU. So you not do the full LU factorization you would do for a direct method, but you do some kind of incomplete. You drop entries, you don't take as many entries, something. Or you do an approximate inverse. That's quite a nice class of methods. So you're actually, the inverse of a sparse matrix, which is irreducible, would be dense, but you can approximate it with a sparse matrix perhaps. And these are using core techniques of direct methods. That's conventional preconditioning. So what I'm talking about in the remainder of this lecture is using a direct code in combination with an iterative method to do a factorization. So that comes on to my main theme. So this is the third time you've seen hybrid. And the intention is that I'm going to really use a direct method, a direct solver. I'm going to use something like, if you've used direct solvers, you'll know these names. And if you don't know these names, I'm telling you they're good direct solvers. So Mumps is the one that you work at, that I work on in France. SuperLU based in Berkeley, Pastix from Bordeaux, Paradiso from Switzerland essentially, and that's used within some projects also in Purdue, or HSL, which is what Ahmed mentioned graciously in the introduction, is a set of codes we've been working on at Harwell and now Rutherford for many years. So this direct solution is not going to solve the whole problem. Well, it might. That'd be great, of course. But normally, in a very big problem, we're only going to solve a subproblem or simplified version. And the idea of a hybrid method is we do as much with the direct method as we can, and then we have to get the full solution, we have to use an iterative method. And I want to just mention that we've been talking about this for a long time. Now, this is a bit of an eyesight test. I just want to see if you can see. There's a certain guy's name here. If you see this name just here. So this was a young fellow that I was writing to, or a young Gare fellow that I was writing to in Illinois at that time about a visit I was making to CSRD in 1989. But in that talk, or the talk I was offering to give there, I talk about hybrid methods of solutions. So this was going back a good number of years. But I thought I would show that to show that I really did speak to Ahmed, to your Conte professor, I should say, some time ago. Long before he knew he was going to be in such an exalted position in Purdue. So one aspect of all this, of hybrid again, I mean, this is my theme, you could say this is a theme slide almost, is that it maps well onto hybrid or heterogeneous systems and gives great hope that it might scale. So as I mentioned, we'll use the direct code on either a subproblem or a nearby problem. And this is a simple example. If I've got a matrix which I can split up into diagonal blocks, here I've got a few off diagonals, then I could solve this as a block diagonal system, and even if you're only in 101 parallel computing, you should have an idea how you could get a nice level of parallelism out of that. So you solve that in parallel, and then all you have to do is to make a little adjustment with a simple iterative method to pick up these few non-zeros off the diagonal. And normally you'd expect, if you have about 7 iterations at worst, you would pick up all these. So this would be called block Jacobi if you were doing a factorization of these blocks, and then the iterative method could be something like the method I mentioned, GMRes. So that's an example of a hybrid method, simple example. Just to classify them, so this is one slide I'll spend a couple of seconds on. If you don't know the methods, then I'm sure you can go to some nice numerical analysis courses in Purdue that some of the faculty here are more than capable of giving you, and they'll love to do that. Multigrid is again, it's very much a hybrid method where you essentially have, if you like, you can discretize the thing coarser or finer, and you're trying to solve on a fine grid, but the coarse grid approximation you may solve using a direct solver. In domain decomposition, it's not too dissimilar to the method I'll discuss, but there you chop up the region, and then you have to solve on the interface problem, and the local problems you can solve maybe with a direct method. block iterative methods of the kind I just mentioned, which the example was block Jacobi, and you use a direct solver maybe on the subblock, so we're combining it, hybrid, direct, and iterative. You could have a partial factorization. By that I mean that you take not the matrix itself, but an approximation to the matrix, and you factorize that as the preconditioner, or you factorize a nearby problem. So there are various kind of flavors to it. I should mention here again, just to keep happy with my hosts and so that I can escape with my skin intact tomorrow, that there is a nice Purdue-based hybrid method, and I was very pleased to have some time on the plane coming over to read more carefully about it. This is a project led by your famous current Samuel D. Conte professor. And it's called Pike, and if you don't know about it, I suggest it's worth talking to him because it's got all the attractiveness of a hybrid method, and that's what I'm also trying to promote just now. And they call it hybrid method as well, which is very nice. And basically, well, I'm really characterizing it very briefly here, but they've got a very efficient parallel method for solving band or variable bands or sparse band systems, and they use a parallel direct code. They use that code I mentioned called Paradiso, and then they can use that effectively as a preconditioner for BiCG, another iterative method for solving them. So on the last... yeah, this is actually, I must be speaking nice and fast. I forgot to ask if you understand Scottish.
Only if the Scotsman is wearing a kilt.
Ah, well, you know, it's interesting. If I'd known what the weather was going to be like, I might have worn a kilt, because a kilt is really a winter garment. And when I left England, it might have been raining, and it still is apparently raining, but it was quite warm, too warm for a kilt, really. But the weather we had yesterday was very kilt-like weather. So I'll make a note in my diary that if I come to Purdue again, I might try and bring my kilt. But if I do wear my kilt, I'll probably speak even faster and with a stronger accent, so it could be worse. And then the problem is that with a kilt, you have to have your ski and do. And ski and do is a small dagger that you carry, and the airlines don't seem to regard that with this due deference, you know. Even if I told them this was a religious object or something, I think I might have a problem getting it through security. So, back to Camino. This goes back a long way, just like some of the earlier slides. I was working with some of these guys back nearly 20 years ago, and we decided we'd done enough at that time. But now, because of some new technologies and because of these approaching machines, we're looking again at this range of methods. So the BlockCamino method is actually quite simple to describe, I hope. And what you do is you take your matrix, and this is meant to be a big matrix. It doesn't have to be, it certainly doesn't have to be symmetric. It doesn't even have to be square. And you slice it up, chop, 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 into P segments. And then I've got to put a pseudo-inverse here because this is not a square matrix, right? And then I just solve each of these P systems quite independently. Totally independently, and then I just take a linear combination of them to update my solution vector. So it's a really simple algorithm. Does it work? Well, remarkably, it'll work. It always converges. Unremarkably, it can converge so slowly that you could well be waiting into the next century to get a solution. And we're quite early on in this century or just now, so it's not a very fast method by itself, necessarily. You might be lucky. Depends on the matrix. But that's the basic system. Notice that, and just to emphasize, that the individual problems are of this shape, right? Underdetermined systems. You've got the full vector here, which I'm going to later make a linear combination to get the updated vector, and I've got this part of the residual or the right-hand side there. So how do we solve this? We're going to use a direct method for solving it. At the moment, it's not the only direct method. We could use some kind of sparse QR. AI is very sparse, of course, everything's sparse. It's just been chopped up. We've got no fill-in or anything. So the way that we do this, we're solving here the AI on this side, right? It's the same equation as I had before, and I can solve it using this augmented system. The augmented system is symmetric and indefinite, but square, all right? And we're going to use the direct method. In fact, we're going to use the mumps code partly because that's something that I've been developing, and also it's in the same group in France that we're working on the BlockCamino on. But you could use other methods, as long as it would handle the indefiniteness. And notice that one of the kind of definitions of hybrid methods are if you just change your sizes. In other words, if I just had one partition, then I would have a direct method. It would just be a direct method. It wouldn't be very efficient if I did it this way, because I would have doubled the size by having my full A in the both parts here. But that's really an essence of hybrid methods, that by changing something, you end up with a direct method. And that's what I say at the bottom here. It really is extending a direct method. This is perhaps as mathematical a slide as we've got, which isn't, I hope, too taxing. And the point here to show is rather important. So I've just rewritten again the iteration matrices. That was the residual one. That's the rectangular matrices. Just regroup them so that I've got the xk's together. That's all. Then put them into the matrix Q. And the final equations that I'm solving here are given by this here, where psi is just equal to this series of vectors here. And the H matrix, as you notice, is a sum of projector matrices. So the H matrix is going to be positive definite, and therefore I can use conjugate gradients. Conjugate gradients is an iterative method designed for really for symmetric positive definite matrices. It's a Krill method, and it's extremely efficient and good method to use, and that's why we love to have positive definite matrices. And here we have, remember, our original A was completely anything. It could have been rectangular, certainly unsymmetric. It wasn't any properties of it at all, but this H matrix is symmetric positive definite. So this is the aspects to BlockCamino. Partitioning, I showed you slicing it up. I haven't talked about doing that. I'll mention a couple of more things. Solution of subproblems using a direct method. I get a symmetric positive definite system, so I use a conjugate gradient acceleration. And of course, I've got some preconditioning connected with the conjugate gradient acceleration, or connected even with the solution of the subproblems. So I've got all these aspects to play with. And the great thing here is that one's always looking for having topics for graduate students, of course, when you're a professor. And there's more than enough scope here for keeping about half a dozen graduate students working 24 hours a day, or longer if they're energetic, you know. Just a quick thing on the on the partitioning. So let's suppose we've ordered it so we've got a block tridiagonal system. These come quite naturally at times, and then we chop it up a bit. Now we've chopped it up by taking at least 2 block rows together, and I notice that this part of the matrix and this part going down 2, there's no overlap. All right, if you look up the columns, no overlap. They're sort of independent. I can rephrase that this way. Same sort of thing. I've split it up again, and these subproblems here are block independent. So they're completely in parallel, and if you like, the projection, some of the projections of the projection on this space is just the sum of the projections, okay? And similarly for this part here. So the only issue I've got in convergence is the interaction between this block and this big block. So we call it a 2-block partitioning. And you can prove a lot of things with the 2-block partitioning, and it was done mainly by Tommy Elfing back in the 80s. The main aspect is that the iteration matrix will have its largest eigenvalue is positive definite, as I mentioned, so its smallest eigenvalue is greater than 0, and its largest eigenvalue is only 2. And indeed, most of the eigenvalues are clustered around 1, and I think, if I've still got this right, I don't like this way of doing things. I can't see what's coming. Yes, I'm right. Good. So we have a nice picture here. Lambda max is 2, down here. Big clustering around 1, which is around here. And then the eigenvalues tail off here. Smallest one's about 10 to the minus 10, 7 times 10 to the minus 10. So that's really quite good. This matrix is order 57,000, and it's only got 129 eigenvalues below the lambda max, which is 2 divided by 100. So that looks pretty good, but in fact, you know, there's a lot of business here affecting convergence, and when you do try and converge, you note a couple of things. You note the conditioning, because if you see the difference between the backward and forward errors is quite dramatic, and you notice the plateau, it's pretty flat. This is just conjugate gradient acceleration. We do tend to use block conjugate gradient, which helps a lot, but nevertheless, there's a problem here. So how do we, what do we do for this? Well, what we do now is that we want to try, and there's two issues. One is in the direct solver, it can be quite nasty, the Camille conditioning there, and the problem in the direct solver is the direct methods don't like the symmetric indefiniteness, because the main ordering and organization is based on the fact that you can choose your numerical pivots in the direct method freely, and for a positive definite system, there's no problem there, but when you get indefinite, you get a problem. So that's the first issue. And the second issue is that, I should be looking up here, the second issue is that you've got this problem between the blocks, which is roughly what I was showing in the last slide. And I want to just illustrate that, I think. Yeah. Sorry, I've been so busy today, I haven't looked at these slides for 2 days, since yesterday, so I'm glad that this is the same thing that I saw yesterday. Otherwise, it could really be embarrassing. So here we have like this is just 2 dimensions, 2 subspaces, 2 lines here. And we've got a point here, and we're doing orthogonal projections, and we're trying to get to this solution here. And you can see what happens. I project orthogonally onto that. My eyesight's not very good. That's meant to be orthogonal. Back onto this, back onto that. And you can see that I'm going to zigzag for quite a long time, i.e. a lot of iterations to get to convergence. So let's suppose I've got a method of just forcing these subspaces or these lines apart. So I do that. And bravo, look at this. Nice projection to there, projection down onto this. The angles have gone a bit skewy here on this, but never mind, it's roughly about right. Then projection back onto this, and then, you know, we've solved it in very few iterations. So it really does help to widen the angle between the subspaces. That was just a little illustration. Okay, so we're going to do that, and then we're going to force orthogonality. We're going to get a condensed subsystem. And we're going to call this the ABCD method. And this ABCD method was actually, what was our French graduate student that suggested that, which I thought was quite brilliant, given that the French have a habit of any acronym you can think of in French is the opposite normally to what it would be in English. So NATO is OTAN, for example, and other things of that kind. And here, so maybe it should be the DCBA method or something. Anyway. Take our matrix, this is our typical matrix. We're now going to try and force orthogonality. So we're going to take additional variables here, right? We've got additional variables, and we're going to choose these so that we're looking at the orthogonal, or the angle between the 2 subspaces A1 and A2 in this case, or AI and AJ in general. We're looking at that space. If we then take it off again here, you'll see that if I look at this, compare this expanded system against that expanded system, do the product, then because of the I here and the C1, 2 being the same as this, it becomes 0. So these 2 block rows are now orthogonal. Yahoo! So we've done what we want to do. And I've got the same thing for these 2 rows as well, and for these 2. So in this expanded system, which I'm calling A bar, in this expanded system, all these strips now, all of the strips, not just every second one, all of these strips are orthogonal. And by orthogonal, I mean really orthogonal. So what does that mean? That means I need 1 iteration, and I've solved it. Ah, brilliant. So that's what I call a really good iterative method that requires only 1 iteration. So I've done that, but I haven't quite finished yet. I've got to get a system that gives me the same solution as the old one. So I add some more equations to build up. And y will be 0 because of the second set of equations. And this will give me, as you see, a solution to the same solution, AX equals B. All right. So the problem I've now got is that these ones I've just added, they're not orthogonal to the first plot, or to the first splitting. The ones here. So that's easily overcome in a way. I just project, this is just the projection, of the y was the this here, okay, that part. In order to obtain W, and W will now be orthogonal to all these previous ones. You can show that. So now I've got this system. This was the W matrix, BS. This is the original ones, AC. This matrix has all the partitions in the top part plus the bottom partition are all mutually orthogonal, and so I don't need any iterations, essentially. I have to, the right-hand side has to be then updated to this to get the same solution. And the overall solution I'm going to obtain is given by this solution here. This A bar is that one with the augmented top part. This is the bottom part. The W plus I can define, I can show to be by fairly simple algebra, which I'm not going to go into, but is given by this. Now look at the solution, and I'll just spend a couple of seconds looking at that. So what we've got here is we're solving the overall system. We've got a very simple, non-iterative, if you like, part, which is just running through these projections, solving each by direct method, but they're independent, so I can do that, get this solution here. That's just the projection matrix caused by that. The y's are just the nothing zero matrix. That's the same as this, so only have to do that once. So the only thing I'm ending up having to do extra is solve for this matrix S. What was that matrix S? That matrix S was the second part of the bottom bit, this bit here. Okay, and the matrix S had some nice properties. Look at that, positive definite, got some nice things about it. Right. So now let's concentrate a bit on S. This was the size of S matrix in that big 57,000 by 57,000 chemical engineering problem from Bayer, the people that gave you the aspirin. But they didn't have this matrix when they gave the aspirin, because that was about over 100 years ago, I think. So the size of S, that's the crucial thing. If S was small, we're in business. Look at the size of 3 of our nice test examples that we have here. This is a dimension. That's the number of partitions we use. We play around with that a lot, but this is an example. Size of S, well, sometimes it's pretty good. Here it's even bigger than the original matrix. So we can have potential problems, I think you can see. The other problem is that S is not necessarily a well-conditioned matrix. It reflects the conditioning of the overall problem. Several possibilities. The one that we would look at, normally do, is to use a direct method on S and form it explicitly, but we don't have to, because S is symmetric positive definite, so we could use CG. The very, very final comment is, what do we do now? Okay, now I've got about 3 slides on this. We're going to drop entries in these blocks Cij. We could have just tried to reduce things in S, and we have done that, and that didn't work too well. But now we're going to drop entries in these blocks to try and reduce the size of S. What happens? Well, the problem is that we lose some of this nice numerical orthogonality we had. That's why we chose it. But we can lose it in a controlled way by not dropping too many entries, and we'll show what happens. And this is what happens. So here is from our matrix again, and this is an example of the size of S, right, against the filtering level I'm doing on C. So overall, the main problem originally was 2, 4, 6, 9 columns, which is up here. And you can see that quite dramatically, it depends on the problem, of course, but quite dramatically, as I increase the drop level for C, I really reduce fantastically the size of S. So let's look, you see. By this time here, by point 1, I've got it down to 7, 8, 4 columns, 3, 6 columns, 3, 5, 4. Now, I would expect, of course, as I go along here, I'm actually going to get worse orthogonality, or lack of orthogonality, and more iterations, and worse eigen distribution for the iteration matrix. So just to show this in 3 cases, this was the first lot, which was really a big drop down to here, and then we'll look at a couple more. And you see here that we've got, well, I can't really compare it against anything because I haven't shown you other things, but this is actually quite good. You can believe me or not, as the case may be, but I'll show you something that's worse in a minute. You can see that the number of eigenvalues below lambda max. It's not 2 blocks, so it's not 2.17, but the number of eigenvalues are very few that I've got to worry about. And then we move to the next one, and you can see that what's happened is we've just literally done a little worse. This was the previous, that was this one. We had to rescale it, of course. So this one's coming in here. So it's getting a bit worse at this point, but we've now got S down to 360 columns, which is becoming really quite small, given that our main system is 57,000. Okay, but we can go a little bit too far, and then it becomes even worse. It's not really converging very well now. The eigenvalues are going to pieces. We're down to 254, but perhaps we don't want to go that far. So that's the sort of status that we're at the moment. I'm assured by my student, since I'm far enough away, he can assure me of a lot of things. But he's assuring me that everything is working in hunky-dory now, and we're going to get lots of nice results very soon. So you can watch this space. So the conclusions are that the main theme for the talk I've just given is hybrid. That's the word to walk away with. Hybrid machines, hybrid programming. And these words are used for using mixed OpenMP, MPI, everything else, hybrid solvers, and you've got examples here in Purdue as well as the one I've just talked about. And I'm pretty convinced that they are the route to scalable sparse solvers. And I hope this APCD method will be included, and we've still got to get more data on that. It's work in progress. And of course, the crux is going to be this S matrix I mentioned, but I'm kind of got some confidence. Whether there's any reason for it, I don't know. We'll find out. And there's also a huge amount of parallelism in the methods. I have another talk that talks about parallelism and how sometimes you can get lost there because the methods itself aren't very good. Here, the basic method, BlockCamino, is not great, but there are many ways of accelerating it, which we've already looked at 20 years ago, and we're looking at more now. So hopefully that's going. So I thank you, and I wish you all the best for the next 50 years. Thank you.
We have some time for questions, comments.
So one of the other problems with these exascale machines is that nodes are going to fail pretty frequently.
Mm-hmm.
What can you do about node failures or solving an iterative method?
Well, first of all, I buy my machine from a vendor who's going to help me a lot with this, because there are two issues. There's the mean time to sort of failure of chips and things. But the thing that really concerns us is what we now term the mean time to interrupt for your program. So it's something that hasn't been picked up. So, of course, the benefit of the main problem is not actually handling the failure, it's knowing a failure's occurred. So if you know a failure's occurred, I mean, you've got sort of natural checkpointing built into any kind of iterative method in a way, because you've got the previous iteration of that. So you could recontinue from that point. I'm not sure, and this is something we could have a long debate about with some of you guys that are more computer science oriented. I'm not entirely sure how big initial resilience or fault tolerance is, to be very honest, to people like me in the street who are trying to run something. Some people are telling me that even on an exascale machine with like 1 billion cores, the actual mean time to interrupt will be maybe in the order of a day. Now, I can do quite a lot of computation at 10 to the 18 floating point operations a second in a day. So I don't know how, I really don't know. I like to sort of stick my head in the sand until the sand gets too hot. I don't know. But I think the methods that we're looking at, because they have a kind of block iteration, they're maybe a little bit more robust if you can indeed identify when things have gone wrong. When we're calculating residuals all the time, I mean, we can see if something's going funny. I mean, if it suddenly is, I mean, these methods always converge. BlockCamino, this is a great thing. It will always converge, maybe slowly, maybe very slowly. But so we can tell if the thing is not converging, that something is going funny. So that's the best I can say, really. But it's a very fair point. Yeah?
Is there any special preconditioner
Well, yeah, the preconditioner, there's two levels of preconditioning, really. The preconditioning I've been spending most time on has actually been a preconditioner to try and help the direct method solve the indefinite problems. And if you remember, I had this augmented system, this is going to be, which has got, yay, there we are. Now that's the speed of doing a talk, isn't it? Yeah, yeah, actually I went too far. Yeah, oh. Yeah, so in fact, basically that matrix I there, I can replace that by a matrix G, and then the preconditioning matrix is actually G transpose G for the Camino system. And that comes then into affecting my augmented system. What I choose for that, well, again, I can look at the subspaces and try and choose diagonal or block diagonal matrices that are trying to squeeze subspaces apart. So there are techniques for getting good preconditioners, but they are a bit ad hoc at the moment. And again, this is the whole theme of the whole way of getting block projection methods to work, or projection methods to work, is to try and squeeze apart the subspace you're projecting on, really.